We're asked to use the delta y over delta x method of example 5 to compute the derivative of the following function at 0, and we're assuming that this a value right here is constant, meaning that as x changes, that does not impact what happens to a. A is just going to stay exactly what it is. Okay, so let's go ahead and do that computation. What we need to do is to find delta y over delta x. We're going to look at f at the initial point plus a little bit minus the function at the initial point all over delta x. And then, kind of hidden in the background, we are also going to let delta x become really small. Okay, not 0, really small. Okay, so let's go ahead here. This function is f of something is equal to 2 times something plus a, where a is just some number. Who knows what a is? Okay, but it's a number and it's given. Okay, it's already picked and we're not going to change it at all. And so that means that f at x plus delta x, so we'll come back here, f at x plus delta x is 2 times x sub naught plus delta x plus a. That, folks, is this part right here. Okay. Now we need to subtract off f at x naught, which is 2x naught plus a. And that is here. Okay. And then we're going to go through and we're going to divide by delta x. So we need to distribute this 2. And distribute this negative. Just like that. And then if you notice up here, this 2x naught cancels with this negative 2x naught, and this a cancels with this a. So the a's cancel out. In fact, they didn't matter at all. We could have put b here, c here, whatever we wanted right here. It didn't matter. Look, because it disappeared. In fact, it's always that way. Whenever you have a constant at the end, it's going to disappear. And the reason for that is because that value at the end only shifts the function up or down. It doesn't change the slope of the function. And we're looking, when we look at the derivative here, we're looking at slope. Okay? I want to put this in here because it's important. So the derivative as a function of x naught is now equal to 2 delta x over delta x, or just 2. So what we've found is that the slope of the tangent line at any point on this function right here is 2. Well, that makes sense. Look, this is a linear function, right? It's got a constant slope. If we take a look at 2x plus a, let me just graph that guy out for you real quick. Let's assume that a is positive just for argument's sake. So here's a. And here, this, I know it doubled up on me, but this is f of x equals 2x plus a. Well, if you grab any point on this line and you look at its tangent is the same slope as the original line. So this tangent must also have a slope of 2. And that's all we're trying to get at here is that, look, if you have a constant function, the tangent lines all have the same slope as the original. I shouldn't say constant function, a linear function. They all have the same slope as what the original function is. Okay, and that should be pretty obvious. Now you don't see that so much in the algebra here, but you definitely see it in the picture, and that's why it's important to draw pictures out so that you can really get a good feel of what's going on in the background.